Hello, today we're going to talk about the relationship of principal open subsets to localization and the spectrum. And we'll prove the lemma, which I already mentioned last time. So let's state it again at first. So let's look at the map from the spectrum of the localization at the multiplicative subset 1f, f squared, and so on. And we have spec phi to the spectrum of A. Again, A is a ring as usual. And this is induced by localization. So what I mean by that is just that let me write it in a new line. So we have the map phi, which maps A to A over 1 in the localization. So this goes from A to AF inverse. And the claim is now that this is an open embedding with image d of f, which is the spectrum minus the vanishing of f. Okay, that's the first claim. And the second claim is that the A algebra A localized at f inverse is initial among all A algebras such that the induced map, so from spec B to spec A, so induced map means, we have an A algebra, so we have a map from A to B, so we get also a map from spec B to spec A, and so this is initial among all these where the induced map vectors over this principal open subset. And I'll tell you later what initial means. This is just some term from category theory. Okay, so let's prove the first part. So under the spectrum map, so we have the following correspondence, namely primes in the localization correspond 1 to 1. Let me call these primes P, to primes in A where F is not in P. Primes. So here I need, let me see, primes P in A, or P subset A, such that F is not in P, and this just maps to phi inverse of P. Okay, so as we've seen or mentioned, we know that this is continuous, so we get a continuous. So this is just the spectrum of A minus the vanishing of F. So that's quite clear because the vanishing are these where F is in P, so we get this bijection, and we know that this map is also continuous, so we get a continuous bijection on this principal open set D of F. And we have to show that it's a homeomorphism onto the image. So what we want to show is that it's closed onto the image. So if we consider it as a map onto the image. Okay, so let's show that it's closed. So let's take some closed set in the spectrum of the localization. And again, all closed sets are of this form, where M is just some set, and we write M as some AI divided by Fi to the Ni, where AI are elements from the ring A, Ni are non-negative integers, and I is just some index set. Okay, and now we define another set, namely the set of the enumerators. So this is just a set of these AI. This is a subset of A. And the claim is that if we apply spectrum of phi to the vanishing of M, that this is the vanishing of M prime intersection with D of F. And that, of course, is a closed set in D of F. So that would show that it's a closed map. Okay, so let's prove the claim. So let's take some P in this V of M, which is a subset, again, of the spectrum of AF inverse. Now let's look at what happens to that P. So we have that it gets mapped to the inverse image, so under this map phi. So this is again a prime idea, and use a new line. So that's just the set of A in A, such that A over 1 is in P. And I claim that this is an element of the vanishing of M prime. So that's a claim at first. Let me show you why it's true. So what we want is that AI are in phi inverse of P, so for all AI in M prime. And what do we have? Well, we have AI divided by Fi to the Ni is in P for all these AIs. So we get that AI over 1 is in P. So that means just that AI is in phi inverse of P. So that's what we wanted to show. So we have that inclusion, and now let's prove the other inclusion. So let's take some prime in the spectrum of A, and namely not just in the spectrum of A, but in this principal open set intersection with the vanishing of M prime. Okay, by virtue of being in D of F, we get that P is some, so it's in the image as we've shown before. So that's for some P in the spectrum of the localization. And it's also, well, we can write it as phi inverse of P. And what we want to show is that this P is actually in V of M. Okay, now let me also write it down. So we want P in V of M. And again, we have now AI is in phi inverse of P. So we get that AI over 1 is in P. So for all AIs. And by being an ideal, so this step was also by being an ideal, we get that AI over Fi to the Ni is in P. And this means that P is in V of M. Okay, so that proves part 1. So now let's prove part 2. So let me tell you what it means for I to be initial. So let's take I to be an object of some category C, and you can just think of some, let's say, abelian group or something. Yes, maybe you think of an abelian group and try to think of if there exists an initial object in the category of abelian groups. So that would maybe be a good exercise. So, and the property of being initial means that for all objects in the category C, there exists a unique morphism from, call it. So there's just a unique morphism from I to A. So yeah, we get this unique morphism. And now let's see, let's look at the statement again. So where do we have it? So the A algebra. AF inverse is initial among all A algebras such that the induced map factors over D of F. Okay, so let's see. So we have, what do we have? Well, we have A map spec B. We have D of F and, well, just the inclusion into the spectrum of A. And now, what do we want? So we have A. We have, let's call this map from A to B psi. We have again phi to the localization. And we want a unique map here. So that's our universal property, or that's the property of AF inverse being initial among these. And of course, psi, so that means, so this map psi has to fulfill this here, so that it factors over D of F. Okay, so let's see how we prove it. So let's take some element of the spectrum of B. Now let me first tell you some notation. So we will also use this in the future just to make life easier. So we don't write spec of psi for maps in the future, but we'll just write A psi. So that's shorter and that makes life easier. Okay, so we have this pi in the spectrum, and then we have A psi of P is in D of F. Well, that's just the assumption. So now let's apply F to this, and when I mean apply F, that's again in the usual sense. So we look at it modulo the prime ideal, so F modulo the prime ideal, and I claim that this is not 0, but that's exactly by being. So this is just rewriting the previous line. So that's actually an equivalent. So what this means is that F is not in A psi of P, which is just psi inverse of P. oops, I didn't want this. Okay, and I claim, again, that's quite easy, that psi of f of p is not 0. So psi of f is just an element in p. And well, that means that psi of f is not in p. So that equation means psi of f is not in p. And well, we see easily that f being not in the inverse image is equivalent to psi of f being not in p. So that means that we have this equivalence. And well, now we have the previous lemma from the previous video. So let me maybe show you. Where do we have it? Okay, so we have that f is invertible if and only if for all elements in the spectrum f of x is not 0. Okay, so here we have psi f of p is not 0, and this is for all p in the spectrum. So that means that psi of f is invertible. So it means it's in the invertible elements. And so we actually get, so we just have to use now the universal property of the localization. So that means so let me show you. So we have this map from A to B. We have these maps, and I claim now that there exists a unique map by the universal property of localization. And this unique map exists if every element from the multiplicative set in A maps to an invertible element in B. And the multiplicative set in A is now 1 f squared, and so on. And now by psi of f being invertible means also that psi of f squared and so on, 1 maps already to 1. So all these elements are invertible. So in B, so we get that there's a unique map here, and that's what we wanted to show. Okay, that's it for today. I'm not sure yet, but probably in the next video we'll start with discussing sheaves, and yeah, probably starting to discuss sheaves. And yeah, the goal is to define so that we get Spec A and a structure sheaf, let's call it O. And then we want to show that if we define a suitable category, we get a equivalence of categories between rings and affine schemes. So that being an affine scheme. And of course we also want to define schemes then later using affine schemes. Okay, that's it for today. Thanks for listening and have a good time. Bye.